Here's another video for the lecture Intro PDE. In this lecture we present section 1.4, weak solutions. Let us recall the problem which we met at the last section, namely the problem of crossing characteristics. So if we draw the picture, and if we have two values, x1 and x2, then we calculated the corresponding characteristic lines. X is equal to x1 plus t times f prime of u0 of x1, and we assume that the slope here at x1, the smaller value, is larger than at the slope of the larger value. So x2 plus t times f prime of u0 of x2. Then we have here a problem. Because on this we have u is equal to u0 of x1, and here we have u is equal to u0 of x2. And this gives here a contradiction. So this was the problem which we met in the last section, and now we present some kind of solution of this problem, because we consider more general solutions. Consider more general solutions. More general solutions. This is the idea. And we call them weak solutions. Call weak solutions. Okay, so solutions. So this is the idea. And now, what is a weak solution? A weak solution is a function u which obeys this integrated form of the conservation law. A weak solution satisfies only the integrated form of the scalar conservation law. Of the scalar conservation laws. So what this means, that for all intervals AB, we have that this equation here is fulfilled. This we derived from, we saw that by this equation we get this consequence. Here we derived this, and now we assume that this holds for all intervals. So this means weak solutions. So d by dt integral ab u of xt dx is equal to f of u of at minus f of u of bt. Okay, so now why this is more general? Let's derive now a condition. So we at discontinuities. We consider now a discontinuity. So we have here, the idea is, we have here again this picture, and now we have graph of y of t, and this should represent a discontinuity. U is discontinuous at the graph of y. Yeah, so at this line it's discontinuous. Okay, and then now we take here this interval, and then we calculate here these integrals, and we calculate now. Let's do the calculation. Yeah, let's try to calculate this. Okay, so clearly we can split up this integral in two integrals. Yeah, from this part and this part. Yeah, so we obtain these two parts, and of course, since this is linear, this derivative is just the sum of these two derivatives. Now we have a dependence on t on two places, here, and also here and here. So yeah, by the chain rule, we know we should take here first the derivative with respect to this place, yeah, of this integral. We can use the fundamental theorem of calculus. Yeah, the derivative of an integral whose upper boundary depends on on x. Yeah, then by the fundamental calculus on t in our situation, this is just the derivative of this function times, and then we have to insert. So we get this term here if we differentiate here. And if we differentiate here, yeah, then we can clearly put in the differential inside the integral by continuity and get this term. So we get this term plus this term, and for here we get a minus, since it's the lower bound by the, so for this reason here we get a minus plus this term. Now we abbreviate the limit when x comes from the left. We add an L, and if x comes from the right, we add an R. Okay, and then let's do the whole calculation. Yeah, inside this intervals, of course, we assume that u is differentiable and solves. Yeah, the scalar conservation law. Okay, so we can we insert here the scalar conservation law. Okay, what we obtain here, this is the first term, yeah, and the second term gives this term here. Yeah, this gives this term, and now if we insert this here, then we can use again the fundamental theorem of calculus, and we get this boundary terms. Yeah, from here we get the boundary term from a, since a minus, with plus, and here we get the limit from the left, but with a minus, and here at b, at y, a minus, and lower bound is a plus, a limit from the right, yeah, since we integrate to larger numbers, and the b. Okay, so we get this expression. Now, this should be equal just to these two terms. So the condition is this must vanish. Yeah, so we get y dot of t times what we have is ul of y of t minus ur of y of t comma t plus, well, maybe I reverse here the order, yeah, and then, yeah, sorry. And yeah, okay, then we also have this term, f of ur of y of t comma t minus f of ul of y of t comma t. This should be 0. This is the condition. Yeah, and since this is a discontinuity, this is non-zero. Yeah, otherwise, also, if these are equal, then it's continuous. Okay, so we can assume that this is non-zero, and then we get this condition. Yeah, we just put this on the other side, or put this on the other side. You reverse the this difference, get a minus, and then divide, and then we have this equation. Yeah, this is called Rankine Hugin-J conditions. Yeah, so the derivative of the line of discontinuity, yeah, this is fixed, is given by the values at the boundary, by the values at the boundary. Okay, let's consider an example. Yeah, let's again consider Burger's equation. Okay, here t and here x. Okay, 1 and yeah, here 1. Okay, here first for this lower values, yeah, for this lower values, the slope should be all. Also in Burger's equation, yeah, we have f prime of u is equal to u, yeah, because f is equal to 1/2 u squared, so f prime is the identity. Yeah, so the slope is always just the value. Yeah, so for smaller values, yeah, we have here by slope 1. So these characteristic lines, they look like this with slope 1. And for in between, now maybe if x is large, then it's 0. Okay, and if we look at these lines, yeah, here, this is the equation for the lines here. Also, for x larger than 1, it's just constant, doesn't depend on t. Here it has a slope 1, a derivative 1, and here it has this derivative. Now look for these lines, all these lines. If we insert t equals 1, yeah, then what we get? We get x plus 1 minus x is 1. So these are all lines which go just through this point 1, 1, 1. Yeah, so in between we have these lines, all the lines which all go through this point. So we see the first crossing of characteristic is here. Yeah, first crossing of characteristic at t equals 1 at this point here. Yeah. So how can we now construct a solution? Yeah, also, okay, here we see until this point we have a nice solution, and so we calculate this homeomorphism. We can solve this equation. Yeah, also clearly we can solve y is equal to x plus t, so we get x is equal to y minus t, and in this situation we have y is equal to x plus t times 1 minus x, and if we solve this for x, yeah, then we can write this as x times 1 minus t plus t. So we have x is equal to y minus t over 1 minus t. Yeah, so this is here. Here we will replace again y by x, and yeah, if y is equal to x, then we of course have y is, yeah, so we get then in the last case we get this. Yeah, these are just this homeomorphism. So we see up to t equal 1 we have a nice solution. Yeah, up to this we have this nice solution. But we have here at xt equals 1, 1. We have a crossing of characteristic. Yeah, and not only two lines, but infinitely many lines cross. Now, can we use the Rankine-Hugin-Yot condition to find a solution also after this crossing of characteristics? Yeah. Okay, so here we have this line and this line, and here it's 1 and 1. Okay, here of course u is, yeah, for large values u is 0, u equals 0, and here u is equal to 1. Now let's assume that yeah, if we look here, if we look for a solution with only one discontinuity, yeah, because here are also here we have different values, but until here there meets only values 0 and 1. So it's reasonable to assume that we have a solution which only has, after t equals 1, values u 0 and 1. Also, is there a solution for t larger than 1 which takes only values u in 0 and 1? Okay, then we have of course a discontinuity here. We have a discontinuity, what does this now gives? F is 1/2 x squared, so we have yeah, on for the smaller f from the right limits, they come from the larger values, then it's 0. Yeah, so this should be 0. So we have y prime is equal to 0 minus, and if we insert 1, then we get 1/2. F is equal to 1/2 x squared f. Yeah, this is f, not f for Burger's equation is just f of x is 1/2 x squared. Okay. Okay, so minus half, and here we have 0 minus 1. So the slope is 1/2. Yeah, so it's exactly in the middle between these two slopes. So continues like this, and here it's 0. Yeah, so we may draw this here, let's say. And okay, yeah, also the solution looks the solution is in this domain 0 and this domain 1. Here in between it takes all the values between 0 and 1, but here we have this line of discontinuity. Line of discontinuity. Yeah, until here. Okay, this is so we get indeed a solution. Yeah, we get indeed a solution, and which is written here. Yeah, this line here. What is the equation of this line? The equation of this line is, yeah, we have y is equal to 1 plus 1/2 of t minus 1. Yeah, because it should go to 1, 1. Yeah, and okay, so this is this equation here. Yeah, from there. So this is exactly this solution. Now let's consider another example. Let's consider here. Now let's consider another example. Again, Burger's equation. Yeah. T x, but this way it's other way around. Yeah, we have here 0, u equal 0, and here we have u0 equal 1 here in this part. Yeah, so here we have this characteristic lines, and here we have this characteristic lines. So this part in between, we do not, this characteristic lines do not meet. So we have some freedom here. Yeah, how to choose the solution. Yeah, and of course, again, we can just choose the line, this line of discontinuity. Yeah, x equal t/2. By the same calculation, we know that the slope should be 1/2 here by this calculation. Yeah, the slope should be 1/2, so we can just define the solution, which is here 0, 1, here u is 1, and here u is 0 with discontinuity. But there exists another solution. Yeah, and this should explain the solutions are not unique. Solutions are not unique. Yeah, we have another solution which also fulfills the the ranking Hugenot conditions. And how they look like? Okay, they are similar. Here they look like they are 1. Here they are 0. But in between, yeah, so here u is 1, u is 1, here u is 0. But in between, we just choose the lines which go through some point. Yeah, what does this mean? If we have here some point x, and t, yeah, so then the value should be just the slope. Yeah, so here u is equal to x divided by t. Yeah, because this is the slope. Yeah, so in between we have this. Yeah, and this is a continuous solution. This is of course continuous. And since it's continuous, yeah, also it's constant along all lines. This is how we construct it. So it really obeys the scalar conservation law, and it's continuous. So the ranking Hugenot condition for continuous solutions are clearly fulfilled. So it's another solution. Yeah? So we see the solutions are indeed not unique. And for this reason, yeah, we introduce another condition. Yeah, we want to allow discontinuities only if there exists no continuous solution. Yeah, so in such a situation, yeah, where the characteristic lines do not go through some region, in this situation we always prefer the continuous solution. So this means we allow only lines of discontinuities if we have this inequality, yeah, which ensures that that we have some crossing of characteristics. Yeah? This inequality means, yeah, that we have some crossing from characteristics. So this is an additional condition which we now introduce. Okay, so and then now the claim is, yeah, okay, so we have this Lux entropy condition, yeah, where at all lines of discontinuities, of course we assume that the lines of discontinuities are separated by some y which obeys the ranking Hugenot condition, and in addition we assume this condition, yeah, which in this situation here is not fulfilled, yeah, because here this slope is larger. Okay, so we have this condition, and now we have a very nice theorem that these two conditions indeed imply that the solution is unique. Yeah, this is what we want to prove now. Yeah, now we claim that, okay, we have f, we have to assume that f is convex. Burger's equation, for Burger's equation, f of x is equal 1/2 x squared. Convex means second derivative is positive. yeah, which f2 prime is of course 1. Yeah, so it's positive. So it's strictly convex. Strictly convex. So we have this condition, and then the claim is whenever we have two admissible solutions in L1, yeah, such that for all fixed t they belong to 1, yeah, then this is monotonically decreasing. Yeah, in particular, if it's 0 at the beginning, it has to stay 0 along the whole flow. Yeah, because of course this is non-negative. It's monotonically decreasing. So if it becomes 0, then it stays 0. Yeah, so if it's initially 0, then it stays 0. So if we fix the initial value, then initially it's 0. So the initial value problem has a unique solution. Yeah, of course, only under this additional assumption that the solutions belong for fixed t to L1. Okay, now let's look at the proof. Yeah, let's look at the proof. So yeah, so we divide R into maximal intervals. Yeah, maximal intervals A of t, B of t, with the property that U is larger than V. Or vice versa, V is larger than U. Yeah, such intervals. Okay, then in between there might be some domains where it's 0. This doesn't play a role because then this difference is 0 in any case. So in between we get no contribution. So we calculate. Now we calculate, yeah, the contribution of this u t minus v t L1 d by dt for these intervals. Yeah? So we calculate this for these intervals. Okay. At the boundary, of course, this means that at the boundary this either vanishes or changes sign. Yeah, that we switch to another interval. Now, the first thing is to show that the boundaries are differentiable functions. Yeah, this A. We prove this only at A. Yeah, at B it's completely analogous. Okay. If one of these two functions are discontinuous, yeah, discontinuous at E, yeah, then by definition of admissible solutions, yeah, because the discontinuities should be graphs of differentiable functions. So then A is differentiable. Yeah, so we may assume that both are continuously differentiable at A of t, because otherwise we automatically have that just by the definition of admissible solutions. It's differentiable. Okay, now both are continuously differentiable. Then now we know then they solve this problem. Yeah, then they solve this our equation. And since they are constant, along these characteristic lines, so if if we have a point where these two functions agree, yeah, then these points are preserved along these characteristic lines. Yeah, u of x equal, sorry, it depends on t. So u of xt equal v of xt is preserved along the characteristic lines. Yeah, and so this is preserved along the characteristic lines. But this means, yeah, because this in both directions, yeah, for small positive and negative times. Now, if we have one point, also if we go for small times in the future or in the past, maybe I should say, for times in the future and the past. Yeah, because these characteristic lines, of course, they also go to the past. So, but this means that this also means now that u is not equal to v. Sorry, maybe I should say u. Yeah, u of xt not equal to is also preserved. Yeah, because if it becomes equal, then it has to be equal in this for small times in the past or in the future. So this is also preserved. Yeah, so we preserve this condition. Yeah, and now this clearly implies that a dot of t is then equal, because at the boundary, if both are continuous, they have to be equal. So this means we just have f prime of u of a of t comma t, which is equal f prime of v of a of t comma t. Yeah, so we have this equation. Yeah, so we have indeed this equation. Yeah, this equation here. Yeah, and this proves the claim. So now we know they are the borders of these intervals are differentiable. Okay, now we want to do the calculation. Before we do, so we know, yeah, that by our assumption, f double prime is larger or equal to 0. So f prime, or maybe more general, yeah, maybe we do it more general. F is convex, so this means f prime is monotonic increasing. So let's look at the Lax equation, at this Lax condition. This is monotonic increasing. Yeah, and since this is monotonic increasing, we know this implies, yeah, that UL of xt has to be always larger than UR from xt. Yeah? By this condition, there is something in between. So we have this condition. Yeah? So okay. Now let's do the calculation. Yeah. Now we calculate this contribution of this interval. Yeah, and we consider only intervals with u larger than v. Yeah, for the other intervals we may just interchange u and v and do the same calculation. So we, without loss of generality, we may restrict to this case, u larger than v, because otherwise we interchange u and v. Yeah, and now we do the calculation. Yeah, okay. We again calculate this this derivative. Yeah, and then we get again this boundary terms here. This boundary term and this boundary term, and yeah, by the chain rule, if we do this differential, also we get of course this term plus this boundary terms, yeah, also from this term we get sorry, if we here we should do the chain rule, yeah, then yeah, by the fundamental theorem of calculus, yeah, we get here u minus v times b dot, and here with the other sign. So we get this expression. Now what we do now we insert the differential equation, yeah? And then we know that this is the same as this and this, and now we again may solve this, and then we get this equation here. Yeah, so we get this equation. Yeah, if u and v are both differentiable at a, then they take the same values at a. Yeah, so this difference vanishes and this difference vanishes, so this vanishes. Yeah. The same argument applies if they are both differentiable at b. Yeah. Okay, we have here this is a contribution at b, and this is the contribution at a. Yeah? We will distinguish between in the following argument. Now, okay, we already understood this, and of course the same should be true for v. VL of xt larger than VR of xt. Yeah, at all discontinuities. Yeah, at all discontinuities. So maybe we should write here y and not okay. So at all discontinuities we have this. Now, if we have the following cases, yeah, at A and B, in both situations we can have both are continuous, one is continuous and the other one is discontinuous, or both are discontinuous. Yeah, and now first we consider that both are continuous and understand then we get no contribution. Now we consider the situation then one is continuous and the other one is discontinuous. since at the boundary, yeah, the difference has to become 0 or changes sign. Yeah, and we restrict to this case. Yeah, this means the continuous function has to take values between these two values of the discontinuous function. Yeah, because either it becomes 0 or it changes sign. Yeah, so for this reason, yeah, it has to, the continuous one has to lie in between. Now we claim that this situation, that u is larger than v, now only allows two possibilities. Yeah? I claim this: either u is continuous at A and v is discontinuous at A, or u is discontinuous at B and v is continuous at B. Okay, why? This means at A, we claim it's not possible that at A u is discontinuous and v is differentiable. Yeah, because if u is discontinuous and v is differentiable, then v must lie in between. Yeah, at A. But on the left hand side, the difference must be 0 or must change sign. Yeah, the v can be only at equal to the u. But if it's equal to the u, then on the right hand side, v is larger than u are. So u is not larger than v. So you see, indeed, it's not possible by this assumption and by the choice of our intervals that at A u is discontinuous and v is continuous. Yeah, and similar at B. Yeah. Now at B, we claim at B u is, it's not possible that u is continuous at B and v is discontinuous. So if v is discontinuous, then u must lie in between. Yeah, on the right hand side it must be 0 or it must change sign. So u minus u must be smaller than v. So it must be equal to VR. But if it's equal to VR, then it's not positive in the inside, nearby the boundary, u minus v. Yeah? So we see indeed this is not possible. Okay, so we understand by our choice and due to the restriction to this case, we only have to consider, it remains now three cases. One is u is continuous and differentiable, v is discontinuous at A, or the other way around at B, or both are discontinuous. Okay, now let's first consider the contribution of the first case. Yeah, of the first case, yeah, we just use our formula here. We use our formula at A, so this gives our contribution here, this term. Now here we have to insert v is discontinuous, so we have to take the right limit, so we get this. Now for A dot, we'll know by the Rankine-Hugin-J condition, this is this quotient. So we replace this by this, and then we get this formula. And so yeah, we write this at this formula, but now you see we have that v that u is the continuous, u of at is in the interval, yeah, is in this interval. So we are for at and VL. Yeah, this is larger of AT. So it lies in between. Now, what is this, this expression here? This is the value, and I claim this here is, moment, this expression, what is it? So let's draw the function f. Yeah, we have here f. We have here VR of AT, and we have here VL of AT. This is larger because we have a discontinuity, and we have our convex function. Yeah, and here we have these values, and now I claim, and we have some u of AT in between somewhere. Okay, and now I claim that this expression here, this is exactly the linear interpolation at u alpha of t. So it's the point on the connecting line between these 2 points, the secant, and the line which intersects, yeah, the graph of f at these 2 points, and evaluate this here. Yeah. So by convexity, this is clear, since if this is equal to the right hand side, yeah, if this is equal to the right hand side, then this vanishes, so we get just this, and if this is equal to the left hand side, then vanishes this, and then we get this. So it's just a linear interpolation. Okay, so we see that this value here is larger. So the whole thing is non-positive, yeah, by convexity. This is non-positive. Okay, now, so we have understood the first case. Now comes the second case. Now at B, if it's the other way around, yeah, if it's at B the other way around, then we again insert this formula and get this, and then we get the same picture, yeah, with u and v more or less replaced. Yeah, so we get this expression, which is here. Now we should insert here ur of bt and ul of bt and v of bt. Yeah, and then we have the same picture, and again, yeah, this is larger than this, so it's non-positive. So both are non-positive. Now let's look at the third situation. If both are discontinuous. Yeah. Now we come to the third case that both are discontinuous. Yeah. Then okay. Then we claim that the Lux entropy conditions imply that on the nearby A we have this. Now why is this the case? Yeah, because we have UR of AT. Yeah, by the Lux entropy condition, we have UR of AT is smaller than UL of AT, and at L, either the sign must change, or yeah, and we have that UL of AT, yeah, because this is outside of the interval. Yeah, there we have smaller or equal to VL of AT. So all together we see indeed that UR is smaller or equal, yeah, is smaller or equal to VL of AT. Yeah, and why it's larger. On the right hand side it's clear Yeah, but this is of course because inside the interval, it should be positive. So at the boundary, it must be at least equal. So we have this inequality and this inequality, and this shows, this together implies that UR of AT in fact belongs to this interval, to this interval VR of AT and VL of AT. Now what's the case at B? At B it's the other way around. At B we have that VR of BT is again smaller to VL. It's VL of AT. And we know that VL of T is of course smaller because then we are on the inside of the interval of UL of AT. But UR, now we are on the right hand side, so this should be both B. Okay, on the right hand side, then we are outside of the interval, so then the sign must change. And if the sign changes, then this is larger or equal to UR of BT. So we see indeed that this must lie in between. So we see that this implies that VL of BT belongs to UR of BT and UL of BT. So we have these two conditions. And now we do the calculation at A. And then if we insert this, at A, if we again insert this and use again the Hugenot conditions, then we obtain, replace this by the Hugenot conditions. Here we use V for the Hugenot conditions. Okay, so we obtain this expression, and then we again have that this is the value at the connecting line at, here we are here at UR, the middle point. This is the value, so again this is non-positive. And finally for B, we use the Hugenot conditions for the U. And then we have this, and then we see that this is the value of the connecting line, on the connecting line at this point. So this is again larger than this, so this is non-positive. So now we have shown that in all cases, all contributions are non-positive. And this proves the claim. This shows the theorem. And so we have indeed proven this theorem, and this shows uniqueness of admissible solutions. Uniqueness of admissible solutions. Admissible we introduced the notion of admissible solutions. I forgot to mention this. Let me do this. Here we call admissible solutions which only has discontinuities along C1 paths and fulfill both conditions, Rankine-Hugenot conditions and Lax entropy condition. these are admissible solutions. Yeah, and we used all these conditions and showed this, so this gives uniqueness of admissible solutions. Okay, there also exists a proof for the existence of admissible solutions. Yeah, but this is a little bit more complicated, and I do not want to do it here in this introductory chapter. But I have given here a reference. Yeah, under some conditions, one can derive some formula, some explicit formula, first for smooth solutions and then take some limits. Yeah, so this is a little bit more advanced argument. Yeah, one first derives an explicit formula for smooth solutions and then take limits and obtains a formula for solutions, and then show that this formula really gives admissible solutions. Yeah? This is the way how this is proven here in this reference. Okay, so one indeed gets unique existence and uniqueness of admissible solutions. Now let's recall. Yes, this is what we have done today. Let's recall. Yeah, we introduced this weak solutions. Yeah, because we had this problem with crossing characteristics, so we introduced weak solutions. Yeah, in chapter 2 we will generalize this. Yeah, we will see that there exists more general weak solutions. Okay, and then we assume that we have a weak solutions along a line of discontinuity which is differentiable, and then derive this Rankine-Hugin-J condition. Then we understood by some examples that this Rankine-Hugin-J conditions doesn't uniquely determine the solution. So, and we understood that the Rankine-Hugin-J conditions allows discontinuities in cases we don't need. There also exists continuous solutions. So we further restricted and introduced another conditions, yeah, which excluded discontinuities if they are not necessary. Yeah, the Lux entropy condition. And then we proved that a uniqueness, yeah, by some monotonicity of this norm, we proved the uniqueness of admissible solutions. Okay, and then I mentioned that there also exists a proof of the existence, yeah, under some stronger conditions, but this we don't reproduce here. So, thank you.